talking about something called neutral point. What is that point? What is that CG location about which there is no moment, everything is balanced, okay? And if I take the CG either side of the neutral point, either it will become statically stable or statically unstable. This is the meaning of neutral point. And in mathematically, neutral point means where dCm, delta Cm by delta alpha, the slope becomes 0, which without taking much of liberty, dCm by d alpha equal to 0. You will find textbook dCm by d alpha is written like this, deba, because it's like a partial derivative, because Cm is function of not only alpha, even elevator, etc., etc. At this point, let's not mix up the issues. You only understand that the slope of Cm versus alpha graph should be negative above the trim point to justify that, yes, this is statically stable. Okay. Now, just few minutes back, I was trying to make you aware that back of our mind, we have aircraft. Though we are giving examples through plates and all, we're using the magic plate of George Calais. So what is the purpose? Purpose is, I should fly at a positive angle so that there is enough lift to balance the weight. Let's say cruise is our equilibrium point. And you know, if lift equal to weight, what does it mean? It means CL equal to 2W by S by rho V square. So whatever altitude you are flying, whatever speed, cruise speed you are having, if you know that, if you know the weight and the wing area, you know what will be the CL requirement. Let's say that CL is 0.2. The CL 0.2 will also correspond to a particular angle of attack, because you know the CL is expressed as CL naught plus CL alpha into alpha. So once I know if it is 0.2, once I know this value, I know what is the angle required. And that is that angle I want to fly. I want to trim the airplane at that angle, which is a positive angle. Now tell me, if my CM/CG versus alpha is passing through the origin, it says the trim is at alpha equal to 0. So naturally for general airplane, I am assuming it has a symmetric airfoil. I am not talking about camber airfoil at all now. Then it will not be able to generate any lift, because it is saying trim at alpha equal to 0. For normal case, I don't want to fly like that, because I won't be able to generate lift. To generate lift in normal case, I need to fly at a positive angle of attack. And now at this alpha, if you want to fly, and I want that it should be statically stable, then means the slope here should be negative. If my airplane has this sort of a Cm versus alpha rather than this, then I can get a positive angle where I can fly with the appropriate speed to maintain lift equal to weight. If I ask you a question, assume that these two lines are parallel, which configuration is more stable, more statically stable? By now you know, when I talk about static stability, I only check sine of dCm by d alpha, the slope of the line, Cm versus alpha, that decides whether it is statically stable or not. But if these two lines are parallel, that means both are having same dCm by d alpha, both the graph has same slope, both are negative, so both are equally statically stable. Then what is the difference? Difference is, if I am having a configuration like this, then I can trim that airplane at positive alpha, because at positive alpha, Cm is 0. But to trim this airplane, my alpha is 0 for a trim. So I don't want to fly like this, because I cannot generate lift in normal case. So I will be interested to ensure that I get positive alpha while I am flying the airplane. So graphically, if you see, what is the difference? Difference is, although these two straight lines have same slope, but their intercepts are different. That is, this line has got positive intercept, whereas this line is passing through the origin. This positive intercept, whatever you are seeing here, I can write this for representation. It is Cm, pitching moment coefficient, at alpha equal to 0. Or notation wise, it is written as Cm naught. So what is the message? Message is, if you want to fly at this alpha, and if your airplane is statically stable, do something in your configuration so that it generates this much of Cm naught, this much of nose of moment. Okay? Now let us take an example to understand this concept. This is a very popular configuration, wing alone configuration, and popularly they are called flying wing. We'll visit our design lab where we'll show you how we are making all these configurations, how we are translating whatever we learn in the blackboard and actually produce it and fly it. That's very important closing activity that will be there in part of this course so that you get a feel.
Welcome friends, this is the flying wing. It is called flying wing because its whole structure is enclosed in airfoils, and in this you can see we have a very large root chord and very small tip chord. As a result, very small taper ratio, and we have a very large sweep angle for the leading edge, and because of this the flow which would be coming somewhere here will get separated somewhere here, and the flow which would be coming from here will get separated somewhere here, and the flow coming from here will get separated somewhere here, and as a result there is very complex interaction between the flows, and the leading edge vertices are formed, which is the disadvantage of the flying wing at lower speed. But as we increase the speed, the flow which had separated earlier, that gets reattached and the leading edge vertices disappears. That's why the flying wings are preferred for high speed applications only. As you already know, for an aircraft to be stable, our aerodynamic center must be behind the center of gravity. That we can achieve by adjusting the weight distribution. If our aircraft is unstable, it doesn't mean it cannot fly. It can fly by giving some suitable feedback into the control surfaces. Like our body is unstable to move on a road, but we can move. At the same time, our requirement is to trim our aircraft at positive angle of attack. In cambered airfoil, we have negative Cm naught. If you remember, in conventional design, we have negative Cm naught because of the wing, but we have horizontal stabilizer. We contribute a large amount of positive Cm naught, and as a result of the whole aircraft we have positive Cm naught. But here we don't have horizontal stabilizer, so we need to ensure something in this design itself so that we have positive Cm naught to trim at positive angle of attack, and that's why in flying wing we use reflexed airfoil. In reflexed airfoil we have positive Cm naught. To control its longitudinal as well as lateral motion, we have common control surface named aileron. It acts as both aileron as well as elevator. When this is deflected symmetrically, it works as elevator, and when this is deflected asymmetrically, it works as aileron. Because we are using common surface for both aileron and elevator, suppose I am giving a climb with a right turn, so what will happen? I will give symmetrical deflection for the climb, and because I am taking right turns, I will reduce left aileron deflection and I will increase the right aileron deflection. So what happens? The right aileron deflection will become very high, and that will enter into non-linear region. Its designing of control becomes complicated because we need to handle that non-linearity which has arise because of entering that deflection into non-linear region. You can also see we don't have any non-lift producing surface. That's why it has better aerodynamic efficiency than conventional design. We don't have any vertical surface and vertical surface reflects the electromagnetic waves very significantly, but here we don't have any vertical surface. Therefore, its reflection to radar waves is very small, and as a result its radar cross section is very small. At the same time, if we coat it with some radar absorbent material, it becomes almost invisible to the radar, and this is the most desirable property in the war applications. Thank you.
Let's say there is a wing which has symmetric aerofoil, the cambered aerofoil, and if I typically I say this is your wing, although in market people will be more attracted by delta wing, triangular shape. I am not talking about those. I am taking a very simple example. So this is the wing. I want to ensure that this wing is statically stable by itself. Okay? So what I have to do, and these are the location where I am putting the aerofoil. It's not really I am putting the aerofoil, not a correct statement. The contour of this wing is decided by the contour of the aerofoil at planar sections, right? And let's say if I want to make this wing alone statically stable, by now you know I should ensure that CG should be ahead of, what do I write? Should I write center of pressure now, or I write aerodynamic center? By now we know that when you talk about aerofoil, we have conveniently found a point called aerodynamic center where you can represent all the forces acting. Why you choose aerodynamic center as a point? Because about aerodynamic center, the pitching moment is independent of angle of attack. Okay? So it's a very convenient point for us. So I will now switch over from center of pressure to aerodynamic center. For a small angle, for our understanding, they are almost same. Although center of pressure changes its angle of attack, right, for general configuration. But let's say for us almost the same concept with little bit of error, doesn't matter. So when you are trying to think, you think in terms of center of pressure. Now we are talking about aerodynamic center, which is basically a point about which the moment is independent of angle of attack, pitching moment, and that is generally the quarter chord point of the wing, and we take it as a point of reference. We represent all the lift coefficient, drag coefficient, moment about that point called aerodynamic center. Now suppose this is the wing and it is to be flown like this. What do you think? This is statically stable or not? We can check. Any disturbance? CL I can represent here, lift I can represent here, and it will give a nose down moment. So it has initial tendency to come back to, or to counter the disturbance alpha, come back to the equilibrium. So I say this is a case of static stability, and by now you are expert, you know the aerodynamic center is behind CG, it has to be statically stable. If I now draw Cm versus alpha, how this graph will look like? That is the question. If you see here, at alpha equal to 0, symmetric aerofoil, wing with symmetric aerofoil. So it will not produce any lift. So no Cm, this point is here. Positive alpha we have seen, it will give negative moment. So here it will. So yes, you are right. Slope is negative. So if I make a wing alone with this symmetric aerofoil, it will be indeed statically stable. But think of, if I now take that wing and throw it with some angle, like this, what will happen? It will try to trim at alpha equal to 0. Because statically stable, the equilibrium point is only alpha equal to 0 here. So it will not produce any lift. It will just go like a projectile and fall like this. No lifting trajectory you will get. Is it clear? Because it is statically stable, even if I throw it with some angle of attack, because statically stable, it will try to come back to the trim point alpha equal to 0. And since at alpha equal to 0, it's symmetric aerofoil, nothing will be there as far as lift is concerned. So it will simply fall like a projectile. Now from here we try to investigate if this wing alone configuration or the flying wing was having cambered aerofoil. Okay. Before I do that, let us understand subtle difference between a symmetric and a cambered aerofoil. Especially at alpha equal to 0. At alpha equal to 0, it is fair enough to make an understanding that whatever pressure distribution comes over here, 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 the top surface if I integrate and the bottom surface if I integrate, okay, they will be of equal magnitude at alpha equal to 0, and their point of application resultant of the lower surface, a resultant of the pressure integrated over the upper surface, the resultant will be of equal magnitude and their point of application will be at same place. So if I am transferring this whole force combination to aerodynamic center, you know I have to transfer it by force and a moment. So this force comes here and a moment, and since they are opposite in nature and same distance they are from this point, so net force or net lift will be 0, and all those moment which I need to transfer when I am transferring a force from that location to AC, they are also in opposite direction, they cancel each other. So at this point AC, we don't have any lift, 0, and also CM AC wing is equal to 0. This is the main point which we are more interested to compare. Now if you see in the cambered aerofoil, in contrast what happens with the pressure distribution because of cambered part, you'll find that if I take the resultant of pressure distribution over the top surface converted into force by taking appropriate area, the resultant will be somewhere at this point, and for the bottom surface it will be somewhere here, not at the same line. So when I transfer this to the AC, you can very well see at alpha equal to 0, since these two magnitudes are not same, in fact this is more than this magnitude, so you'll find there is a positive lift at alpha equal to 0, and also when I transfer this force from here to here, I have to give a moment like this. When I transfer this force to this point, I have to give a moment like this. So the resultant will have a negative pitching moment, a concentrated moment. That is why we write CM AC wing for a cambered aerofoil is less than 0, and for your understanding, the magnitude will be in the range of around this minus 0.01 to minus 0.1 is a fair enough good number to have a feel. So now for cambered aerofoil, how do I write? I'll represent it like this. AC, whatever CL, CD, and CM is the AC wing. This is the convention for positive, but it is a negative value, so this value is minus, let's say 0.08, some value. So as a designer, I understand if there is a cambered aerofoil, since CMAC wing is negative, it will have a natural tendency to come down like this. So CMAC negative means try to put the nose down. So if I now draw a cambered aerofoil, this is the AC, this is, let's say this is the CG, and AC is behind. Now again, if I draw CM versus alpha, CM means CM CG versus alpha about this point, statically stable, so slope will be negative, no issues. But what about at alpha equal to 0, what is the CM? You know, because at AC already CMAC negative is there, so at AC there is a CM AC wing which is negative. Over and above, we are trying to, of course, trying to see what is the behavior at alpha equal to 0, don't forget that. We are trying to find out what will be the CMCG at alpha equal to 0. For a cambered aerofoil, you also know If I plot CL versus alpha, at alpha equal to 0, there is some positive CL, we call it CL naught. So what is happening now? If flow is coming such that alpha is 0, this much CL naught will act at AC. No issues? Over and above, there is a CMAC wing which is negative. So overall moment about the CG at alpha equal to 0 will become more negative. So although this is statically stable, so you will get, let me draw it. What we have observed, if this is the cambered aerofoil, if this is the CG, this is the AC, since there is a CL naught at alpha equal to 0, this will give a nose down moment, plus you know that CM AC wing is also less than 0, that is opposite of this sign. Typical value will be minus 0.08, minus 0.05. The point to understand is, if I plot CM, CG versus alpha, now at alpha equal to 0, what will happen? At alpha equal to 0, this CL naught will give a nose down moment, which is negative. CMAC is already negative. So at alpha equal to 0, I will get some value here. However, since AC is behind CG, it will have a CM versus alpha slope negative. So if I draw it like this, it will look like this. And the condition where CM equal to 0 will happen at alpha negative. Left hand side. Please understand, whenever I write CMAC wing, I give clockwise arrow as a matter of convention for a positive direction. But I know by number the CMAC wing is negative, right? So this CMAC wing and CL naught into this distance non-dimensionalized, that will give a nose down moment. So we know that at alpha equal to 0, I will get a negative moment. My problem is now I don't get a positive angle to trim. For this, for symmetric, the alpha was 0, I cannot produce lift to balance weight, and here it is negative angle. I want to fly at a positive angle. So what is the solution? It means if I throw a symmetric aerofoil wing, that is in a wing alone, having symmetric aerofoil, if I throw it with the angle of attack, it will naturally come to a negative angle and fly like a projectile. If I throw a cambered, again same thing will happen, it will come to a negative angle and fly like this. But my mission is not fulfilled. I want the lift to balance weight for a flying wing configuration. So what is the option? That is the question. So if I just summarize, symmetric, this is cambered. For symmetric, of course, here it is CG, here it is AC, CG, here it is AC. So when I plotted CM, CG versus alpha, it was like this. When I plotted here, it was like this, and this is negative angle. This alpha here is less than 0. This part is clear to us, and both of this configuration is not what we are looking for. That is, if I make a wing alone configuration, whether it is having a symmetric aerofoil or a cambered aerofoil, if I just put the AC behind the CG, that is, I do the mass distribution such that CG is ahead of AC. AC is governed by the platform, right? Nothing to do with the weight. But CG I can change by distributing the weight. So I distribute the weight in both the cases such a way CG is always ahead of our aerodynamic center. So they will be statically stable. But my problem is what? My problem is I don't get positive alpha in either case. But if you want to balance lift equal to weight, in general I want a positive angle of attack. So what is the option? Recall we have just seen that if this is CM versus alpha, and if I want a positive angle of attack, let's say even same static stability, then I must have CM not greater than 0. That is, I must have Cm at alpha equal to 0, positive. If I have a positive intercept and dCm by d alpha is less than 0, then I can fly at this positive alpha, right? So I have to somehow generate Cm naught, but Cm at alpha equal to 0 to be positive. What do I do? Now I check another configuration, which is like this. It is loosely opposite of camber, loosely, but this is called reflex aerofoil. But if you take the cross section of the wing, the shape of or the contour of this will be like this, which is basically reflex aerofoil shape. If it is like this, what happens now? See, so this is again the CG is same, and I put a AC of the wing here. So again AC is behind CG, so no problem, statically stable. I am more interested to see whether at alpha equal to 0 there is a positive Cm naught or not. What happens at alpha equal to 0? It goes like this. Again, go back to George Calais. This portion will be pushed like this in a simplistic manner. So it will give a downward force, and that will give a positive moment about CG. Is it not simple? No, don't think big. Simply air is flowing like this shape is like this. So air will push downward force, and this downward force will give you positive moment, and this is happening at what angle? Happening at alpha equal to 0. So if I am using a reflex aerofoil in a wing alone configuration, I will indeed generate Cm naught, and if I have decided what is the slope of this line, that is what is the degree of static stability I have, I can design my configuration to fly at this positive angle of attack. So in a nutshell, whether you are using a symmetric wing or a cambered wing, a wing alone configuration can be made statically stable. However, you cannot trim it at positive angle of attack. That is why I was telling, we'll be calling this equilibrium point as trim point. However, if you want to make flying wing, a wing alone configuration to not only be statically stable, but also I can trim at positive angle of attack, then I have to use a reflex aerofoil, which looks like this. In a standard aerofoil database, you will get different shapes of reflex aerofoil with different aerodynamic characteristics. So I hope I have been able to make you understand the importance of keeping AC behind CG and importance of having positive Cm at alpha equal to 0 to ensure I am able to fly the airplane at positive angle of attack. So in a summary, when you talk about static stability, we say the slope dCm by d alpha should be less than 0. That means AC is behind CG, if I am talking about just wing alone. And for trim, we will say Cm naught should be greater than 0. Remember, when I try to translate this knowledge to aircraft, I will be using the same concept, but few nomenclature will change. You see what happened? We started with a flat plate. We talked about center of pressure. Center of pressure behind center of gravity, then statically stable. We graduated towards wing with an aerofoil. From center of pressure, we came to the concept of aerodynamic center, because we want a point where I can represent CL, CD, etc. and moment, and aerodynamic center is the point at which Cm is independent of alpha. So it's our choice. We have chosen that point, which is incidentally the quarter chord point. We know that. So from flat plate to an aerofoil based wing, wing alone. Now from here we will go to the aircraft. But please understand, whether it is a flat plate, whether it is a wing alone configuration, the basic understanding is clear that if we want to trim an airplane, fly an object or lifting object which is stable, then dCm by d alpha, the slope of this line Cm versus alpha should be negative. If it is negative, then it is statically stable. But if you want to trim it as positive angle of attack, then Cm naught should be greater than 0. This is the understanding. Cm naught is Cm at alpha equal to 0. This should be very, very clear in our mind. And that is the beauty of this understanding. If you have understood this, you will find understanding aircraft from stability and control point of view is so straightforward. Okay, thank you.